All right. So what anti-differentiation or integration lead to is finding the area of an amorphous blob, essentially, of an unknown region. And again, graphically, we saw that on the E video that it's kind of counterintuitive that, you know, a derivative is the slope of a tangent line and the antiderivative is area, but they're related by the fundamental theorem. So let's say I have this region. It's the graph of y equals x squared bounded by the curve itself above and by the x-axis below on the x interval from 0 to 1. I want to find an approximation for the area of that shaded region S. Well, if you were left to your own devices, you might just say, it looks a lot like a triangular triangle, right? It looks a lot like a triangle. So if I just drew a secant line from here to here, I can just find the area of this triangle using geometric formulas, right? Area is 1/2 base times height. So the area of this region is approximately 1/2 the base. The base is 1 times the height is f of 1, which they give to me as 1. So it's about 1/2, right? That would be a crude approximation. And not only would it be an approximation, but you would also tell geometrically the way you drew it that it would be a what? Over or under. It's an over approximation. So whenever we use secant lines, it's going to be an over or under depending on the curvature of the graph. This one is concave up, so the secant line gets too much. If it were concave down, the secant line would get not enough. So I know that the area of that shaded region is a little bit less than 1/2, right? And that might be good enough for what you're trying to do, right? Maybe. But what if your wife said, my standards are higher. You need to get a better approximation. And they're like, oof, I better learn a better way. Is there any way to modify this to get a better approximation? Huh? Oh, okay. I can split it into 2 triangles. Yeah, I can maybe draw a line down the middle, and then my first triangle would be a triangle. But would the second triangle be a triangle? A trapezoid. There you go. If you just divided it into 2 equal parts, now this is still a triangle with still a little bit of error. And then this one is a trapezoid with a little bit too much. So yes, this actually leads into a trapezoidal rule that we're going to learn, because the first triangle is actually a trapezoid as well, with one of the heights, one of the bases 0. So yeah, and then if you needed a better approximation, you could divide it even into more parts. So having a systematic approach is a lot better than just jumping in and trying to fit shapes into there. If you saw that other video, we know a few geometric shapes for area or formulas from geometry for certain shapes, like triangles, trapezoids, circles, pi r squared, right? Rectangles, squares, all kinds of stuff. Now, the simplest shape is a rectangle, all right? Even though triangles are work as well, they become trapezoids sometimes as we work further down the interval. So what Riemann sums becomes, did the video talk about Riemann? No? Okay. What we're going to be doing is we're going to be doing Riemann sums. It's named after George Bernard Riemann, who was a student of Gauss. He was Carl Friedrich Gauss' student, Gauss being one of kind of the top 4 math people of all time. We call them Riemann sums after this guy. Now it's easy to remember Riemann sums because Riemann sums use rectangles. Okay, so it's rectangular approximation. So I'm going to show you in this one example how we can systematically do that. And then if we needed to get a better approximation, it's a real easy thing to do. What we're going to be doing is kind of, it has the seeds of like primitive programming. Like if you're trying to write a computer program to do it, it's the same kind of thought process that we would do. All right. Okay, got it. So step 1, it says to use 4 subintervals. That's 4 partitions divided into 4 spaces of equal widths to, and then here's the word, approximate. So now we're on squiggle alert, right? Estimate or approximate is squiggle alert. The area under the parabola x squared from x equals 0 to 1. using the indicated methods compared to the actual. Okay, so step one, it says using rectangles using the left endpoint L of 4. Well, before we get that 4, there's a little bit of housekeeping we have to do. We have to gather some information. I want to draw this into 4 equal partitions. So 4 is an even number. So the easiest way to do it is to come up here and draw a line straight down in the middle. That divides it into 2, and then come up to the graph and go straight down in between those other 2. And that's an easy way to kind of visually see, and you get the idea. You're bisecting, and then you bisect each region. Now, what you want to do is draw that vertical line up until it hits the curve. Okay, and here's the left endpoint. Now, you could maybe intuitively figure out the x values that are these stopping points. X equals, x equals, x equals. X equals left endpoint, x equals the right endpoint. Because these are stopping values in our program, we might want to indicate the sequence. So typically the left endpoint we call x sub 0. And then x sub 1, x sub 2, x sub 3, x sub 4, so on and so forth. Okay. Now I got to figure out where those stopping values are. Like if you told a computer, hey, take the span from 0 to 1 and divide it into 4 equal spans. Tell me what those stopping points are going to be. Well, you can figure that out easily, right? You need to figure out the total distance you need to span and divide it by the number of equal segments you need, right? So if I need 1, 2, 3, 4 segments from 0 to 1, that should be 1 divided by 4. All right. So really the first thing you do after you draw it, number 1, you're going to draw it. Number 2, you need to find delta x. Okay, that's the width of each interval. So here's the formula for delta x. It's b minus a over n, where b is your right endpoint and a is your left endpoint, and n is the number of subintervals, partitions that you're using. So for us, we're going from 0 to 1, so that's 1 minus 0 over 4. And it will always specify how many partitions to use when it's like this, okay? It'll tell you. All right, so now I know they're all a fourth away. I can come over here and label them. I'm starting at 0, and then I add a fourth to get the next one. 0 plus a fourth is 1/4, plus another fourth is 2/4 or a half, 3/4, and then 4/4, which is 1. Now I'm using fractions because this could be a no calculator question, but if you want to use decimals, 0.25, 0.5, 0.75, have a good time. Okay, have at it. Now, what do I need those x values for? Well, because I need to figure out what the y values are there, right? This right here is f of 0. This y value here is f of 1/4. This is f of 1/2. This is f of 3/4, of course. And this is f of 1. With rectangles, there's always going to be 3 ways to do it when you have the graph and you have the equation. You could do left endpoint, right endpoint, or midpoint. Now, here's what the left endpoint is. I'm going to use a different color now. On the left endpoint, you're going to go on the first interval from 0 to a fourth. And which x value are you going to use for the height of that interval? Well, the left one. So you go to the y value on the left endpoint, and you draw a horizontal line to the right. That creates the first rectangle, which is flat, right? Then on the next interval, you go to the left endpoint and draw a line to the right. And then so on and so forth. Now from there, you can see the rectangles that I've made. The first one is squashed, but then I have 3 more right here. Now I can immediately tell just by sketching them that if I can find the areas of those 4 rectangles and add them together, I'll get a decent approximation that is what? Too big or small? Too small. And that's because not the curvature, but because the function's increasing. So let's go ahead and write it out. Here's what we're going to say. We're going to say that the area, okay, the area is going to be approximated by L sub 4. We typically use L for left endpoint, and then the subscript kind of tells the user or the observer how many subintervals you're using, okay? So the actual area is approximated by L sub 4, which equals, and now it's just geometry. It's width times height plus width times height plus width times height. So what's the first width from 0 to 1/4? 1/4 times the height. Well, that's f of 0. What's f of 0? 0. Okay. So this is width times height. Plus the next width from 1/4 to 1/2 is 1/4 times the height is using the left endpoint. So that's f of 1/4, which is 1/4 squared. So there's width times height. Plus the next width is 1/4 times the height is the height at 1/2, which is plugging it in, you get 1/2 squared. And then plus the last width is 1/4 times the y value is 3/4 squared. Now notice I never even use the right endpoint, do I? The rightmost point of 1. Okay, but that's just width times height plus width times height. I guess I should put 0 squared here just to make it consistent. Width times height plus width times height. Now I'm going to do this one time. I'm going to show you how you can write that in with symbols instead. This is going to be your delta x times f of x sub 0 plus your delta x times f of x sub 1. I guess I don't need those parentheses. I'll just put it side by side. There we go. Plus your delta x times f of x sub 2 plus your delta x times f of x sub 3. That's essentially what we're doing, right? That gets a little painstaking to write it like that. So that's why I did the concrete first. But now, if you watch the video, you know sigma notation, which looks like a E, it's the capital letter for S. We have a sum of things that have a regular pattern look to them. So we can either expand or condense it using summation formulas or sigma notation. This ends up being the sum sigma, or actually I usually just draw it like this. That's the capital S in Greek, okay? Which in this case means sum, okay? And it's going to be f of x sub I times delta x. Now notice I flipped it around. Is that okay? Each term is delta x times f, delta x times f. I flipped it around at f times delta x, f times delta x. And notice I put x sub I there. I is called an index. And an index is just a counter. It keeps track of things. And so what we typically do then is we say down here from I equaling, what's our starting I value? 0 to at the top, we go all the way to 3. There you go. All right. That's looking good. Now, notice the similarities. This sigma will turn into another S, but it's going to be elongated S called the integral symbol. The f of x sub I, that turns into just f of x. And then the delta x, which is finite and measurable, turns into, guess what? Dx, yep, which is infinitely thin and none. And then the from I to 0 to 3, that's how we read that. The sum from I equals 0 to 3, this becomes from x equals a to x equals b, okay? And that's going to give us the definite integral. That's where we're heading. That's what Riemann did. Riemann took the sum, the finite sum of a finite number of rectangles, I said that twice, to a process of infinitely many, like the limit as delta x goes to 0 in the top becomes the bottom, okay? So it's still built on the idea of the limit. Is that it? We're done? Oh man, so much fun. So we'll pick up there tomorrow, and we're going slowly in the beginning because there's so much theory involved, and you really need to understand geometrically what it is we're doing. And then we're gonna fly. We're gonna fly. Yeah, this is a hugely important section. So we won't finish tomorrow, but if you have any questions on your take-home test, email me. I'll be here in the morning as well when the doors open up. Have a super duper awesome rest of your day.